show you that like these 2 points are like very close to each other, right? Like on that side and off that side. But after I rub it, then these points which were originally very close to each other are like very apart from each other. So that's why it's things that we don't want to happen. Like we want like things that are very close, or in our original coordinate system should be also very close on our surface. So that's why we need to talk about smoothness. And the way we do that is essentially by reducing it to smoothness of the curves. So what we would like to say essentially is like we choose some kind of curve, and then this curve connects these 2 points. And then what we say is that this curve which are like connecting these points should be also still smooth in our original setting. So that's the idea. This one is continuous differentiable, or it's called sometimes C1. If for each point on P and D, and open bore which is like contained in D, the max would be C1 define 2 curves, namely C1 of T, which is just changing the point in slightly in the x direction, and the second curve just only changing things in the y direction. If these ones are smooth in the sense of what we just talked about at the beginning of the lecture. So the idea is again that you have essentially you look at like these red lines and the black lines. That one of them would be this one, the C1 would be like going something in the x direction like this, and these ones would be something that goes like in the black line. And then you look at like how this map is like changing them, and you look at that these curves which are now defined as something that lives in 3 dimensions if they are still smooth in a sense. So that's the definition. And similar, you can say like that something is smooth if these maps down here are smooth. Yeah. And then we need like the partial derivatives. have like the map, and now the partial derivatives say essentially how the map changes if I only change slightly in x direction and if I change slightly in y direction. So we define the change y. And let's just take this curve that we had at the beginning, the C1 curve, and take this one, it's the derivative at some point t, which is like at the point t equals to 0. And similarly, the derivative in y direction is we have the curve that is only changing in the y direction and then take its derivative. And sometimes, but I'm not sure if I will do that, but in some books you might see that it's like denoted by this. So you have d1 of theta, but I think I will always write d phi with respect to the x direction. So phi, or d phi dx is then again a map which takes now points in D, which would be some two-dimensional point, and gives us a vector. So it's again something in 3 dimensions. And similarly, d phi dy is also a map like this. So we can also talk about its derivatives and stuff like that again. So like you take derivatives and derivatives. So we can just iterate that to get higher. For example, we have phi defined to be x and y, to be the map x2 to y x in 0. Then d phi with respect to x, really what you would expect, namely you take 2x, 2y. And the derivative in y direction equal to 0, 2x. So that's like a and now we need something for curves, which was a bit simple to do, but like for surfaces gets a bit harder. For curves, what we had, again, we have like this open interval, we go to some point, and then the curve tells us where on the curve, the map C tells us where on the curve we are. And what we can do, of course, is we go a little bit in a later time. And what that happens is then this point here moves a little bit along the curve to give us another point. And then we can take the infinitesimal version of that to get like the tangent vector at that point. So that's like relatively clear in the one-dimensional case. But now assume that we have something in 2 dimensions, and we would like to do the same kind of trick. Is that we go to a different point, but this time there's like multiple directions where we can change our point to. Here there was essentially just like, say like how much time we go in a certain direction. But here we have like more information. We can say like we go in a certain direction, right? So we need like a whole vector that gives us the direction. And then the question would be, if we map these ones up here, how is then this vector transformed? If I have like this vector down here, I slightly move in this direction, I map it over here, I get up to somewhere there, like what kind of map is that? So, and that's what is called a tangent map, which says that like you give it like a vector in its domain, and then it says like how much is that like changing towards the, like the, yeah, in its codomain, its target. What kind of vector do we get? So it's a map from vectors to vectors, and that's what is called a tangent map. First look at the tangent map for a curve, which we have define the map that it's like a bit of a strange notation maybe at the beginning. So we take t, which is a capital T as an operation, which has some point based on it. So we take say that the derivative at t equals to 0. So that means that we take t equals to 0, and then take the derivative or the tangent map in the direction of v. So v is the small the parameter. In that case, v is just some number which tells you how far you go in the t direction. And it's defined to be the map. You take the derivative of epsilon. When you change the time slightly in this direction given by v, and then you map it over to the curve up there, and then you take the derivative of that curve. So that's a map, and this procedure defines the tangent map. Which is just this map C, which is a real number, and spits out a real number. So it's really like, just like as this picture says, like how is like a vector transformed in the domain, like mapped towards a vector in the codomain. So that's like what is the tangent map. And if you know a little bit of linear algebra, you can check that this one is a linear map. So if you change v essentially here to 2v, then you get also 2 times the whole vector, but a chain row. So like you can feel as the tangent map also as something like the linearized map of C. Like the curve C is linearized to this map. So for curves, it's not too much, like there's not, it's like not much interest because essentially it's the first derivative, right? So you can calculate what this is by just taking the chain rule, so we get v times the tangent of the curve. So it's just like taking the tangent of the curve and scale it times this v. So there's really not much value doing that in the one-dimensional case, but in 2 dimensions it gets more important or more interesting. Now we can talk about the tangent map of the big capital phi, which was defined on some open subset of P. And similarly, we say the map. So we need to say like there needs to be some base point, which would be now some point in the base D, and that's like the base. So it's a tangent map at point P. So it's and that's a linear map again, and here it was like defined in R because we essentially had like one direction that we could change to. But now it's like mapped that like maps from R2 into R3. Is defined by the formula where we say we take TP phi in some direction V, and we would like to essentially use this formula again. So what we do is we take dd epsilon at point t equals to 0 of phi. We now have p1 plus epsilon v1 and p2 plus epsilon v2. So here we have p equals to p1 and p2, and v equals to v1 and v2. So it's really this picture here. It's like you have a point P. You take some vector at that point which gives you some direction. So that's this. That V over here. And you do that for small, like you consider the curve that like slowly goes in this direction. And then you map that to a point for some time later. So you end up, so you say you do that for like 1 second or something. You end up like over here on that point, and then you do it for 2 seconds, and then you get a curve up here. And this curve, which I draw, is this one here. This one is a curve, if you take it for epsilon, which starts at P1 and P2, so it starts at phi of P1 and phi of P2, and then we take the derivative of epsilon, so we take the tangent direction of that. So it's really this tangent map is essentially mapping this is the small vector V here to this red vector over here. And for calculation purposes, we can actually calculate this further. So this one is like the curve. We can use the chain rule. Say that we first take the derivative in the first direction, and then we take the derivative of the second direction. So we hold one of them fixed, and then take the derivatives. But then you see that these ones are exactly these curves that we defined earlier up there. So if you write this, what happens is then that we get V1 times the partial derivative of phi at the point P1, P2 in the direction of V1. And now we get the same time V2 partial derivative at this time in y direction at P1, P2. So this formula that I wrote now is very similar to this formula here, where we have V times the tangent map of the derivative. Just that like this formula gets more interesting or a bit more complicated because now we have 2 directions in that we can change. Like there's a certain direction in the x direction and a certain amount that we change in the y direction, and that's given by the V1 and the V2, and then we get contributions in both of these directions. And what you can see is that it's like V1 times a certain expression plus V2 times a certain expression. And if you see something like that, then it's usually handy to write this as a dot product of something. As a matrix product. So, and the matrix that corresponds to that is the Jacobian. And this one is the matrix where we collect all the data of so we call it, this is really like a vector, right? So it's really it's V1 dx1 times V2 dx1. And then the same thing. So it's really like a matrix. In this example that we had before, I'm not sure if it's still there. Yes, in this example over here, we already calculate these vectors. One of them was 2x, 2y, and the other one was just having the x there. So in this case, this matrix would be 2x, 2y, 0, 0, 2x, 0. So it's a matrix, but the matrix depends on the points. So you can also view that if you want as like a map from the points to certain matrices, which tells you then how the map changes in x direction and how it changes in y direction. And once you have that, the Jacobian is connected to the tangent map via this formula that we just take the Jacobian matrix and let it act on the vector. So you can also think of the tangent map as nothing else than the Jacobian acting on the vector. So it's like you can think of that as an alternative definition. But so you have two different ways to think of the tangent. One of them would be really as like this definition, where you say like you have v. Let's change our point slightly in v direction and see how phi changes under this change. That's very geometric and usually a very nice, intuitive way to think about it, but not very practical to calculate. Way easier to calculate is to do that, where you say like, okay, I have a map that depends on x and y. I take the derivatives in x direction. I get a certain vector. I take the derivative in y direction. I take a vector, and then I just multiply that or apply it to v. So that's usually a way easier to calculate, but has, in my opinion, less conceptual idea of what is actually going on. But like to work with that, this formula is the easiest. Okay, so now I would like to define what a surface is. But there's one more point that we need to discuss first, and that's about regularity. So we don't want to talk about irregular things. Regularity, or for surfaces, is usually it's called non-degenerate. So for a curve, let's take that as our starting point. We say that C is regular. Now we have to, like, the idea is to redefine that as like something for the tangent map. So first of all, we said that this one means that C of t is never 0. So that was the definition, right? So let's rephrase that in terms of the tangent map, which says that if you take the derivative of the tangent map in the direction of v, this one is never 0, except if v itself is 0. So now we can, because this one essentially was just v times c dot at t. And then, of course, this one is not 0, except when these ones. So what this means is that this map, or better, its image, is one-dimensional, right? So you have like something that is like changing in one direction, and then it means that like you always have like at least one dimensional change. So it means that the image, which are all vectors in R3, such that they exist a number in R such that C equals to is one dimensional. So we formulated now that C is a regular curve if and only if the tangent map has like at least a one-dimensional image. So that really is nothing else to say that like whenever I move like this V is, so if I change slightly the time, then I also have to change somewhere on my curve. I can't stay at the same point. I'm not like degenerating to being like zero-dimensional where I move in time, but actually I stay at the same place. So that's like just like the mathematical rephrasing is that like a curve is regular if and only if the image of this tangent map is one-dimensional. And now we can like use that as a definition, or like the same idea of regularity for our map phi. So we generalize it and say like smooth map phi defined on some open subset taking values in R3 is non-degenerate if for all points that are contained in D, the image of the tangent map, which is now a map from R2 into R3, is two-dimensional. And because the tangent map was defined also in terms of the Jacobian, you get an equivalent rephrasing to saying that this one is equivalent to these two vectors So we want these vectors not to be zero, which would say like that if they would be not zero, then at least one of them is not zero. That means that the image would be one-dimensional at least. So it would be zero-dimensional if these two vectors would be zero. It's one-dimensional if these two vectors are not zero, then it's one-dimensional image, but we want it actually to be two-dimensional. So that means that both of these vectors are not allowed to be zero, and they are also not allowed to be a pair anyway. So the geometric thing is really that I want, like, if I change this coordinate system in the red and the black lines, and I've changed them slightly, then I need to get something two-dimensional. What I don't want is that, like, one direction is like curved, like so small that it's essentially degenerate to being like a circle or like a one-dimensional object. Okay. I'm running out of time, but at least I want to give you the definition, the final definition for today, and that's of a surface. So a parametrized surface is a non-degenerate injective and smooth map and it needs to be defined so that's the definition. Let me go through each of these words again and say, like, really they're super important. So first of all, like open subset means it's like a sheet of paper essentially without a boundary. That's needed to say even what is smooth. Smooth means, again, that what is not allowed to happen is that this thing is that, like, nearby points are like ripped apart and end up at like very different places. So that's why we want like smooth. Injective means that like 2 points are not mapped to the same point. So what this would look like here is that we have like the original points, and if I move them so that they kind of intersect, then I have, like, for example now here, they intersect, so I have like this point and this point, but like in the real space they occupy the same point. So that's not allowed. So we don't want like these self-intersections. So that's why we need like injective. And a non-generate means that really like what I want is like something two-dimensional and not something that's like degenerates to be like a very small line and I only have like one direction. So that means like I really talk about something two-dimensional, which is like makes sense. Why do I want to talk about surfaces? So there needs to be some two-dimensionality. And I don't want to, like the non-degenerate means that essentially I don't lose the 2 dimensions. Like here I have 2 dimensions and the non-degenerate says like whatever I map to is also in some way 2-dimensional. And so, yeah, these are like the, like all the important ingredients. An example would be really like everything I can do in a very smooth way if I like just turn like a sheet of paper. That would be a parametrized surface. You can think already as like a little bit of a homework. For example, the cylinder and the sphere and things like this that you know, if these are like parametrized surfaces or not. Okay, then enjoy your holidays next week. example, what does it mean? Like, if I like take this point in there, and I map it like here, right? So now these, like this one, now we can talk about movements, but like, what is like this variation in this direction on this part? So like, that's why we need like this whole piece. Yes.
I want to know that the one-dimensional means that the third element.
Like one-dimensional.
Yeah. What's it?
Do you have like linear algebra?
Huh?
Do you have linear algebra?
Yes.
Yeah, so there's like, you have the notion of spaces, of a vector space. Yeah, so it means that you have like one vector in your basis, then it's one dimensional. If you have two vectors, then it's two dimensional. And if you have three vectors in your basis, it's a number of linear independent vectors in your vector space.
I know this, but we want to know how can we get the third from the first one, from the C.
If that one is not zero, then it means that this map, it is just like taking the scale of V, first this vector, is also not zero. So this map can't be zero. It means that at some point, take for example, V equals to 1, and then I get a non-zero vector. And that one I can scale and then get my basis. It's non-zero vector, it means like it has to be a one-dimensional object. It can't like a non-zero vector. So that's like this conclusion that like this space where I say like there exists a vector such that it's hidden vector. And if that one is not zero, then there's definitely this one is like the Shang vector. If that's if this one is not zero, then it's one-dimensional. And if that's actually zero-dimensional, that means that this one always has to be zero. And that means that like this expression always has to be zero regardless of the v. So that means this expression has to be zero or v. So then you
定住一个点，没有那个1小时，对，它就是一个切线，它就是切线的长短而已。对，就是一个切线。
说，但是他已经在克制自己分析了，因为他已经在好好写了，他真在哪里？他真的在好好写。
This space here is just the image of the change. Space. Like you take the derivative, changing the derivative, and you take the linear span. Just like the direction of the tangent. So this one is like nothing else than just r times the derivative. So you're at some point and you take the derivative and you look at like the one-dimensional object that is like but of course it's only one dimensional if you don't see it. If you see at that point, like if the curve is like something like that, it's sees at one point, it doesn't change, then just will be zero. So you don't have like a direction is not moving. 我觉得是一，不然的话，你这 GR 是一个零线，然后 add 就是那个 A 不等于零。That's like what it's saying, like the curve is vector, it has to be
是 T， 所以有时候就乱了。它只是说有一个系统性特定的 T。
The surface is the same that you have like in the surface, you always have like two directions. You don't want them to be like forwarding each other. The same way that you don't want like here where you essentially forward one dimension where you say that okay, I'll stay. 然后单色，然后手里的什么就是定这个地方在一起，那你要定在。So you don't want like that's like your point. Like now you have like a mathematical sense as up here. What you don't want is that a curve that goes in this direction is only like mapping in one direction. Even if you say like up here, if we are going in this direction, like if I move in this direction, I also I mean that could happen, right? Like if I give you a general map, then I could say like whatever you do, for example, which is x and y, and I say it maps to x0 and 0. And regardless of what you do with y, I'm always mapping into something else. So we don't want something like that. 那不是那一个是 k 可以 t 点 t， 然后是一个 k t 点 t 下来，然后下一个 t 点 t 点。That's not the curve. We would like to have something that looks easy.
一个平面，
So we need to do our
映射过来不会把它全给折掉。你这一块如果全折掉的话，你的图片会倒。
那你也不是保证它实时
一个平面，然后映射到，比如映射成这样弯的都没问题，如果映射成这样折掉，这个位置的那两个偏旁有折痕的。
可以把，对，我觉得你可以把那样一条，它那不是，它是解出来一个这样的图，就是只要有人，它这个东西等于一个 e 的多半 a t， 但这个不是对，不是 e a t 减去其实跟小的
不好思考，没有搞清楚。你要问啥问题？
And you need this limit to exist. And then also that means that it's like a derivative in the first direction, or like the first derivative, and then you integrate it. So the second derivative is another limit of that form, and you'll keep integrating. And like the third one, so like all of the yes, like for our purposes, usually it's the first and second one, because that's like how often we take the word. But I don't want to worry, so that's why I say like anything that you do smooth, and it means like all the words are arbitrary order. Like what you want is like that the image looks like this and not like something like this. Because at these points this limit here is not existing. So you don't want kind of like these TikTok lines, you want something that goes
确实哦。怎么说？你没有想法吗？有想法吗？严复套啊。我觉得还是要有，还是要这个。你不然的话，你连他的摩擦合为一，你不但说明不了他的摩擦合为一，那么他检查这个部位，你现在有其他的原因吗？那个好像是没有问题。他那个要求的就是他那要求就是 T 和那个 T， 那个 T 等于这个嘛，对，他是说给